Hello, welcome back to The Effect. We're still talking about matching here and the many different ways in which we can match two different sets of observations together in order to close backdoors. Remember, we are trying to pick a group of control observations that is very similar to the group of treated observations across our set of matching variables, so that when we think, hey, are there any differences between these two groups that are being driven by a backdoor, we can say, no, we matched on that backdoor. There's no variation between the groups left in that particular variable, and therefore we are going to be able to close that backdoor and hopefully identify the causal effect. So one of the ways in which we can actually perform matching, as we mentioned in the last video, is distance matching. We're basically taking the control variables that we have, or the matching variables that we have, and asking how far apart are two observations on these variables. Now, this is very easy to do when we only have a single variable that we are matching on. In the last video, we matched on the size of somebody's credit card bill in April, and it's pretty easy to tell how close or far apart two different people's credit card bills are. If my credit card bill is $6,000 and your credit card bill is $5,900, then the difference between those is $100. Great. And if I want to pick the best match for me, I should pick whoever in the control group is closest to my value of 6,000, or do some sort of weighting or something like that. But what if we have more than one matching variable? Well, then things get a little bit tricky. We have to think about how we define the distance between two different observations when we have more than one matching variable. Let's say that we are not just doing the size of our credit card bill, but we're doing the size of our credit card bill, and also let's say how old we are. Now, again, let's say that I'm 35, I've got a credit card bill of $6,000, and I have somebody over here. I got two different people. One of them has a credit card bill of $6,000, and they're 60 years old, and somebody else is 35, and they have a credit card bill of $1,000. Which of those people is closer to me? Well, we have to figure out some way of figuring that out if we want to pick a decent set of matches. So the real question that we have is, how can we take these different sets of distances, right? We have one distance between me and everybody else based on how far apart our credit card bills are. And we have a different distance based on how far apart our ages are. And if we want to pick a whoever is closest to me, we want to have an idea of what it means to be closest to me. We have to have some way of combining those multiple distances into a single distance, so that we can pick whoever has the smallest single distance from me as the best possible match. Now, there are a number of ways to boil down multiple distances into a single distance, but a lot of them are based on a metaphor with literal distance in the real world, right? How far apart is this hand from this hand? Well, here is the distance between them on this particular axis. But then also, how about how far are they apart now? Well, we have a distance in terms of how far apart they are on the x-axis, and also how far apart they are on the y-axis. And there's a single actual distance between them. It is this distance right here. Right? We can actually see this working out on this graph. If you have two different matching variables, you can define their distance along one of the variables, the distance along the other variable, and then, if you draw a straight line between them on a 2D plane, you will end up with a single value distance that you can try to minimize by picking the shortest distance between them. And this generalizes beyond just two variables. So for example, let's say we've got three matching variables, and let's go back to my fists here. Now let's say that my fists are right here. Well, we have a distance between them on this axis, x-axis right there. We have a distance between them on the y-axis, this distance right here. And then also, one of them is in front of the other. We have this distance right here. We have three different variables, three different distances, and we can boil them down to just being one distance, the distance between these two, as I go in a straight line between them. And this generalizes even beyond three dimensions into 4 dimensions, 5 dimensions, 6 dimensions. The visuals sort of break down there, but the math is at least relatively easy. So we want to make a metaphor between the distance between the individual variables and a sort of spatial distance, which boils them all down into a single straight line, the straight line between the 2 points. Now, there are a number of ways to actually calculate this. One is called the Euclidean distance, which literally just does the thing that I said in 3D space. You take this distance and that distance, you use Pythagorean theorem, and you sort of calculate out the distance between the points. But more common in matching is what's called the Mahalanobis distance, which makes a slight statistical adjustment, which makes it make a bit more sense in statistical applications. In particular, Mahalanobis distance does this. It says, okay, we got all these distances between all these variables, but some of these distances are actually sort of double counting the same things. So let's say that I have gender as a backdoor variable that I want to match on and thus close. And let's say that for some reason I'm not actually able to measure people's gender, but I do have measurements about how much arm hair they have and also whether they have a beard. These are both things that are more common among men than they are among women, or at least higher values of them among men than among women. So if I use both of them as matching variables, well, I'm sort of counting them as two different distances, right? I'm trying to make sure that we are, isolating just the distance between them, but I'm also sort of counting the idea of being a man twice because it shows up in two different variables. So what the Mahalanobis distance does is it takes those distances and it divides out the correlations between them, which means that both of those variables are still in there as my matching variables, the arm hair and the facial hair. But the sort of man idea is only going to count once. If it counts twice, it's going to get subtracted out. So that is a common way of actually doing the calculation of distance. We have all these different distances in space. We then sort of rescale all of the axes so we can take out the shared elements. So that now every different distance is completely orthogonal to each other. So we have this distance here, which is how much arm hair do you have, not counting the overlap between manliness with arm hair and facial hair. Here is how much facial hair you have, not counting the overlap between the facial hair and the arm hair. And then we'll look at the distance, right? Once we've done that subtracting out, it gets back to that exact same geometric idea that we are literally just having a bunch of points in space and calculating the closest line between them, and that is our count of how far apart two observations are. And from there, it's easy. Now I can calculate the distance between any 2 points. I can say, here's someone with a lot of arm hair and a certain amount of facial hair. Here's someone with a slightly less amount of arm hair and a slightly less amount of facial hair. How far apart are those two observations? And I can do the same thing for every set of observations. For every treated observation, I can calculate the distance to every single control observation. At that point, I can do whatever I want. I can pick the best match. I can pick with the shortest distance between them. I can pick the 3 best matches with the 3 shortest distances. I could construct some sort of weights, where the ones with the least distance get the biggest weight, and then the weights decay as you get further and further away. The key is now I have a single measure of distance, and I can use that single measure of distance to pick matches or construct a set of weights. Now, there are a couple of wrinkles that come along with doing distance matching, and a big one is the curse of dimensionality. So the curse of dimensionality is basically whenever you have some sort of method that's really sensitive to adding a lot more dimensions. And we have literal dimensions here, right? When we are matching on one variable, we have one dimension. How far apart are you on this one variable? When we're matching on 2 variables, we have 2 dimensions, the x-axis and the y-axis. You're different on 2 variables. When we have 3 variables, you're matching on 3 dimensions. We have x, y, and z space. 4 dimensions, 5 dimensions. Now, the problem is, as we increase the number of dimensions, things sort of tend to get farther and farther apart. Take this as an example. Let's say that we are trying to match people in terms of where they are in a building. You have 2 people who are in the same building, and I want to know how close or far apart they are. Now, let's say that I'm looking straight down at the building, and I notice that 2 people that I'm trying to match on are both in the northeast corner of the building. They're in the exact same spot. It looks great. We're matching in 2 dimensions. These people look like they're very, very close. But now, instead of looking straight down, I'm going to sort of zoom out to the side, and I'll notice, oh, wait a minute, one of those people is on the 5th floor, and the other one's on the 1st floor. By adding an additional dimension, I added an additional way for people to be far apart, and now they are farther apart than it looks like they used to be, because I've added more dimensions. So what this translates into is the more variables you're matching on, the harder it gets to find a decent match, which means that distance matching can kind of have trouble once you start adding more and more and more matching variables, in the sense that now all the matches are going to look kind of bad. You add enough dimensions and it's really, really hard to find somebody who's that similar to you on all those different axes. This can be a problem, of course, if we have some idea of trying to pick the worst allowable match, which was the 5th question that we covered in the last video. Because once you add a bunch of dimensions, all the matches are going to look pretty bad. Now, of course, there are ways to deal with this. Some people would recommend, say, hey, the more matching variables you have, maybe get a bit more lax about what the worst match looks like. But it is still something to think about. And in general, picking matches is going to be a lot harder the more matching variables you need, which could be an issue if we think we might need to match on a lot of variables to close a lot of backdoors. But that is the idea of distance matching. We have a set of variables. We can calculate the distances between 2 different observations on the values of that variable. When we have a bunch of different variables, we are now matching in multi-dimensional space, and we can still construct a single straight line that goes between those 2 observations. And the shortest of those lines is the best of the matches. Now, those lines are going to get longer and longer the more variables we add for matching, but there are ways we can still maybe, say we'll accept slightly worse matches when we have a lot of dimensions that we have to deal with. Now, distance matching is not the only way to do matching, and we'll talk about more in the next set of videos. Thank you.